Okay, so let's jump into this sort of the lecture here. So let's just look at it in four different parts. We're going to first talk about recommender systems kind of broadly speaking. Then we'll talk about collaborative filtering in particular, which is one approach and kind of one vein of looking at recommender systems. And then we'll talk about two approaches for collaborative filtering, really three approaches, I guess, but focusing mainly on two kind of broad classes. The first class is user-user and item-item approaches, which are kind of based upon things like similarity and what are called nearest neighbor methods, though we haven't focused on that too much yet in class. And the third is going to be on matrix factorization. So we'll go through each of these in some detail, but I first want to start out just talking a little bit about recommender systems kind of broadly. So you've all used recommender systems before, right? They're kind of a mainstay of modern, large web applications, right? You log on to Netflix, it'll tell you you've watched these things, maybe you'd like these things too. You log on to Amazon, it tells you you've bought these things and you might want to do this as well. Here's actually my Netflix and Amazon pages, so you can probably actually figure out a lot about me by just looking at this, about, maybe I have young kids that, or I could just like these things myself, I suppose, but probably have young kids, right? And so though we're actually not going to touch on that here, there also are all sorts of sort of privacy issues, which we actually will touch on later in class. I think there's enough of this sort of related data science that we should touch on this later, so we'll have a lecture on that later. But obviously, in the course of this lecture, I just want to highlight, you've all used these before, right? You're all familiar with them. They're kind of this ever-present thing of, you've liked these things, why don't you also try out these things? And really, if done well, everyone benefits here, right? Both the company benefits because they give products that you like, and so they're happy because you're paying more money, and you're happy because you're getting things that you like more, right? So ignoring the sort of potential evils of this for a second, if this is done well, everyone kind of does seem to be happier. Now, when you think about sort of predicting this, so how would you sort of predict that I were to buy these things, right? Or that I might be interested in buying these things? So when you think about it, there really are three sources of information you can use to make your predictions about essentially what a user, me, what items I would want to buy. And items here can either mean, products or movies or whatever the sort of site is selling. So there is sort of pure user information, right? These are things that are specific to me, that are independent of all items. That's things like my age, my location, my profession. And there are things that are sort of more pure item information. So that's things like, for a movie, what's the budget? Who are the actors? What genre is it? For Netflix, they apparently, one of their biggest flags, I think, seems to be whether or not they in fact release it, because they often recommend things that they release. But then there are also, so that sort of seems more similar to the features that we're used to in machine learning, right? We're used to features that depend on, here's a bunch of features of a person, here's a bunch of features of an item. So you can imagine, building like a pure item classifier that would predict based upon user features which users like that feature, which users like that item or not. But then the interesting thing about recommender systems is that there's also this other user item information, right? So in particular, we have a lot of history about what items I, as a user, have bought before, right? So not only what have I bought before, but maybe things like what have users most similar to me bought before. And we want to somehow leverage this to expand upon our predictions. So it's not obvious how this fits directly into the framework of supervised learning when you have these features that depend actually on both users and items, right? It's a little less clear. And in fact, it sort of seems unclear whether this is even really supervised or unsupervised learning in a certain sense, right? So in supervised learning, right, we had a label we want to predict. We sort of have a collection of that, or a collection of a training set about the features and then their corresponding label. But here we have, and whereas in unsupervised learning we just have a bunch of data points, and here it's sort of unclear what we have, right? We have some bunch of data points of user item predictions. Are these labels? Are they not labels? It's not quite clear, and we're really not going to worry about it too much. I think it actually sort of fits into the mold, depending on how you frame things. It kind of fits into the mold a little bit of both these two things, and in fact, techniques from both supervised and unsupervised learning are actually similar to this in a lot of ways, in different ways, but. I'm not going to worry about it too much. For the most part, we're going to formulate this just in the same way we think about typical machine learning problems, in that we'll formulate a hypothesis function, a loss function, and an optimization procedure. Now, actually, in the first case, we're not going to do these two ones, because the first type of algorithm we're going to discuss here, which is these user-user and item-item methods, they really actually don't have a training phase. So there's no, you can frame them this way, but there's no sort of obvious interpretation of what their loss function is or what you're optimizing, because actually you don't optimize anything in the strict sense. So I'm actually not going to worry about that too much. I'm just going to kind of define a hypothesis function and say what the predictions they make are. And then I'm going to, for the third technique, which is the matrix factorization approach, I am going to kind of follow this more traditional breakdown about how we categorize these things. Now, I should also mention one thing here, is that there are lots of challenges that we're not going to consider here in real recommendation systems. So one of the biggest challenges, I guess, in modern systems is that while it used to be kind of expected that you would make all these recommendations based upon the ratings that people would give, right? So you'd watch a movie and then you'd rate that movie. The reality is that most people these days don't rate movies they watch, right, or products they buy. I buy tons of stuff on Amazon. I think I've left maybe one review in my whole life, right? It's just not something many people do. But yet, Amazon still knows to recommend that I buy, kids' toys, because I didn't have to go and rate them. I could have kept buying it and just disliked every single one of them that I bought, and I rated them really low. But they probably don't think that, right? That there's some notion in which you tend to go out and buy things that you like, or you watch movies you like. You don't just keep watching them and keep disliking all of them, right? So you have to account for that while not really having a rating. You still have to account for the fact that people are still, kind of giving implicit ratings by their actual just what they order or what they watch. You also want to have this balance of how much do you personalize versus just kind of give generic good items to everyone, right? So there are a lot of movies, say, that everyone kind of likes, right? How much do we want to recommend, what things you're going to like versus just what everyone likes, right? Because a lot of people just want to watch what everyone else sort of likes and what's watching. The other issue is that if I haven't watched much yet, right? If I'm just sort of starting out and I'm only watching a couple things maybe, you have to also sort of balance, maybe you don't have very much data yet to really integrate personalized predictions, so you have to balance between how much do I personalize versus how much do I just tell people, this is what everyone is watching these days. And then finally, there are these huge privacy concerns too, which we will not focus on today, but which we will focus on in a later lecture, I think. And the last thing I want to kind of add historically is a sort of a very interesting historical note here, which was the Netflix prize. So who here has heard of the Netflix prize? This is now almost 10 years old this happened. So maybe like half the class, which is great, because it really is actually a hugely impactful event that happened in exactly this area. I think its impact goes well beyond recommender systems, but it was a recommender system challenge. So this was a public competition launched from 2006 to 2009, and the goal was to produce a recommender system that improved by 10% upon Netflix's current system that they use for making their recommendations. So this was back when. This is very different from Netflix kind of current thing where they tell you, they have all these different categories now, and I don't even understand how they're making those recommendations. They didn't really have stars anymore. They just have things that you based upon your interests, I guess. But back then, they had stars for every movie. You would rate the movies. You actually would get new recommendations when you would rate movies. They incentivized people to rate them. And they had a method for predicting, what people were going to rate a new movie. And they released a very large data set with about 100 million different ratings for users and for movies. And they challenged people to improve upon that by 10%, improve on the root mean squared error of their current best predictor by 10%. And there was a $1 million prize associated with this. So this is actually kind of, it's actually sort of hard to overstate the impact this had on the field of data science as a whole, or at least this sort of competition space of data science. While there certainly were competitions beforehand, there were things like the KDD Cup was a very sort of well-known competition beforehand. This really kind of brought data science and machine learning competitions to the forefront of the public, or at least the researcher consciousness, right? So companies like Kaggle were started after the successes of this kind of competition. And there were a lot of things that, there were a lot of problems, I think, with this competition, but there were a lot of sort of amazing successes too. So things like this general interest in competitions like this as a major avenue for pushing forward the state of the art in at least in sort of data science, if not in machine learning, at least in sort of I should clarify what I mean by that. So you could debate whether this contest really pushed forward the state of the art in pure machine learning, but it certainly pushed forward the state of the art in people solving contests like this. And so actually that has become in itself kind of a little industry. So people also the things like ensemble methods and things like this gained much more prominence due to this competition. And really, it did, of course, spark a lot of interest in collaborative filtering, especially matrix factorization techniques, which we'll talk about last, which were a key part of some of the winning entries here. One thing I'll say, though, is that one sort of lesson from this is this note of ensemble methods here. And what happened was the winning teams for this contest, no one single-handedly could win this contest. So in order to win, all these teams sort of pooled together their predictions without actually disclosing their methodology. They just averaged their predictions or weighted combined their predictions in some other weighted fashion. And the winning teams were all these very big ensembles. In fact, I think 3 teams joined together to form the winning team. And then once they did that, there was a period where where other teams could sort of try to meet the bar as well. And I think basically every other team that was involved in this then pooled together their things together to try to beat that. And they actually essentially tied it. They didn't actually beat it. So they lost because they tied and the other team submitted first. So it was really kind of this amazing social experiment as well as a machine learning experiment. But the history here was really sort of fascinating. It's also kind of amazing, frankly, that they picked exactly 10% improvement, because this contest lasted for 3 years. And if they had picked 7% improvement, right, it would have been over in like a year. Or a few months probably. If they had picked 15% improvement, it probably would still be going on today, because I don't think the data actually has that amount of signal in it, right? Because there's just some noise in ratings. So somehow, I mean, I don't know if it's luck. They might have had a very good sense of what was possible with Netflix, but a nice random number like 10 took exactly 3 years to solve with constant improvement. So it seemed like this is kind of the limit of what's theoretically possible with this data set, and it's really kind of amazing that it happened exactly this way. So it was really an amazing thing. I think it took a long time for other competitions to reach the same level of sophistication as this one. Okay, so with that being said, let's jump into the actually sort of the details of how these things actually can work. So we're going to mainly talk in this lecture about collaborative filtering, which is one technique for recommender systems, which essentially, and the way I'll kind of describe it is that if you have these 3 sets of things here, it basically uses only this one. So collaborative filtering does not, in the form that we're going to use at least, does not use features about users or features about items. It just uses the information about what users bought what items in the past. So the way to think about this kind of formally is you should think about collaborative filtering as taking as input a matrix like this, where the rows in this matrix correspond to different users. So and the columns correspond to different items. What that means is that this first row here, user 1 ranked item 1 or rated item 1 to have a rating 1 out of 5, and ranked item 4 to have the same user 1 ranked item 4 to have a rating of 3. User 4 ranked the first item to have a rating of 4, and the third one to have a rating of 4 as well. So the entries here in this matrix correspond to ratings that users have given to items. And it's really important. It's gonna become kind of I'm gonna use this notation the whole lecture. So it's important to remember that the first element here is always the users. We index over users in the first item, and items over the second entry in this matrix. Sorry, I shouldn't overload that term. We order over users in the first entry, or the first, so the row entries, and items in the column entries here. Now, of course, the main point here is that we won't have entries for this whole matrix, right? In theory, there is some sort of hidden ranking that every user would give to every item. Right? But of course, we don't see that. We don't have someone input, for every item in the universe, what's my ranking of that item. We only observe kind of some very sparse subset of these things. And our goal really is to predict on the other items, the ones that we don't observe, what's our best estimate of what that rating should be. Okay? So you should really sort of think about this as this matrix being sparse, but instead of the unknown entries being really equivalent to 0, they are just sort of unknown, right? It's not like you rate them to be 0 stars. You just haven't rated them before. And our goal, in some sense, is kind of fill in the missing entries of this matrix. Okay, so that's the collaborative filtering setup, and that's the techniques that we're, sort of the techniques we're going to cover are all techniques for addressing that problem. Any questions so far? Okay, so now there are 3 base, and I remember here, we're assuming that the input to the algorithm is only this matrix, meaning that we don't have, features about the people, about who they are, or where they're from, et cetera. And we don't have features about the items either, what genre they are of the movie, how big the budget was, et cetera. We're going to assume that we're trying to do this only from just observing some entries in the matrix. We want to fill in other entries. And in fact, of course, you do want to also, for a full system, incorporate other elements like the features of movies or people, but we're not going to do that here. Okay, so there are 3 basic approaches to collaborative filtering that we're going to cover in class today. The first 2 are kind of similarity-based methods. And I'll explain what I mean by that in a second. But they basically fit into this approach of user-user or item-item similarity methods. So in user-user methods, the basic idea is if I want to predict for me what I'm going to rate some new movie I haven't seen before, I first go about finding the users that are similar to me, where we'll define what we mean by similar. But basically, since you only have this matrix, what we have to mean by similar is they've ranked movies similar to me in the past. So if we have any overlap in our rankings, those should be similar, right? If we've ranked any of the same movies before, we should have ranked them in similar ways, or rated them in similar ways. Then once I find my similar people to me, I'll look for the similar ones that also rated that new movie, and then sort of somehow combine them to form my estimate of what I think that new movie would be rated. So that's the user approaches, and we'll define that much more formally in a second. The item approaches are, of course, just the converse to this. So here we find similarity amongst items. Okay, so if I want to know how I'm going to rate some new movie, I find the most similar movies to that in the data set. And I look then at, for people that have rated both those 2 movies, how do their ratings sort of, and this is sort of tricky to get this right, but basically, based upon movies that have been rated by both people, because you have to sort of have some overlap in your ratings, I want to find the most similar movies, and then I'm going to say, if I've rated, the current movies that I've rated sort of in one way, and people in general rate these items in similar ways, or they're similar, how do I expect to rate this new movie? Basically, as some sort of combination of my existing ratings and then the similar movies to that one. Right? Hopefully, this will be more clear once we just give the definitions, because really, it's just exactly the kind of the flipped version, though I always found the first one a little bit more intuitive when explaining it. And the last one is the matrix factorization approach. So here, what we're going to do is a little bit different from these approaches. What we're going to do instead is we're going to find a low-rank decomposition of the X matrix. So this is very similar to PCA that we talked about last time, where PCA tries to find a low-rank representation of some data matrix. But the difference here is in PCA, we sort of observed all the entries of a matrix, and we wanted to find a low-rank approximation to that matrix. Here, we don't observe all the entries of the matrix, right? So we want to find a low-rank matrix that, instead of agreeing on every value, agrees just on the values that are sort of observed in our X matrix. But other than that, it's very similar. But the fact that we don't observe every entry actually leads to very different algorithms for solving this matrix factorization approach. Okay, so those are the sort of the basic things, and we'll go through them each of them in some detail, and we'll give a few examples as well. And then on the homework, you will actually just implement, or for the 688 question rather, you'll just implement this one. So this will be the homework question, and the other two will be things that you always are good to know, that are always good to know about. Okay, so let's jump into the first two, which are user-user and item-item approaches. Before I start, any questions though so far? Yeah.
Can you please explain again how items are, similarity between items are?
Yeah, I think, I didn't explain that very well. I think this will be more clear when I actually give the formulas for it. But here's the basic idea. So if I want to find how I'm going to rate some new item I haven't seen before, I first find the items that are most similar to that, right? So I find the items to that item that are most similar. And then in some sense, I mean, I'll describe it exactly, but basically what I do is I rate it similar to those items that are similar to it for other similar items that I've also rated. Right? So if I've rated other items and sort of know how I rate those other items, I predict the new item to be sort of similar to the ones I average the scores in some way according to items that are similar to this new item. Right? And I think it'll be much more clear when I formally define it, though. But it kind of makes sense intuitively, right? So basically, I mean, the fundamental idea is, if I'm looking for, and just to make it concrete, if I'm looking to rate some new movie, right, a Star Wars movie, I'll look at similar movies to that, like maybe other Star Wars movies, and rank my new movie to be sort of similar to those other movies that are similar to it, or rate it to be similar to the other movies that are similar to it. Okay. Let's just jump right into to sort of how we do this, though, and then it'll hopefully be a little more clear how this works a little bit more formally. Okay, so like as I said, the basic intuition of user-user approaches is to find other users that are similar to me. Okay, so if someone else has similar to me and they've ranked some new item, then how they've ranked that item is a good proxy, supposedly, for how I've ranked that item. Right? Now, the catch here is that most ways of assigning similarity between users would, in some sense, kind of assume that we do observe both users all their entries, right? So if I want to compute like the correlation between myself and some other user, the way I typically do that is I would look at my row in the matrix that corresponds to all my ratings. I would look at so maybe this is me here. I look at the other rows and compute who is which row here is most similar to me. And of course I'm saying most similar, but in reality we look at a lot of similar ones, not just one person that's most similar. The problem here is that we don't actually observe all the entries of this matrix, right? We don't actually observe all the entries. So how do we compute a correlation between myself and someone else when there's all these missing entries? And really we do sort of exactly what you would expect us to do. In most of these techniques, what we just do is we only compute the similarity between two users for the items that they both have rated. So if this is me here and this is some other user there, I would only compute similarity, and this is of course a small example because there's only one in common, but I would only compute similarity basically between these two elements here. Between the fact that I rated this item number 3 and they rated this item number 3, and so that's how I would compute the similarity between those two rows in the matrix. So what that also means is that sometimes you cannot compute correlation at all between users, right? Because these two there's no overlap between these two columns here, and so we can't really the correlation would be 0 then in that case because there's no actual items in common that they've ranked. And so I should say item by item approach do the same thing, but of course just, I should say by column instead of row. That one is by row. Let me just fix that. Okay. So item approaches will do the same thing, basically looking for similarity amongst the columns here, using the same fact that you basically want to only look at the ones that have been rated, where this has a rating here and this one has a rating there, but the same user. Okay, so for example, I think I said this before, but if this is me here, who would be my nearest, who would be the most similar user to me in some sense? Which one? The second one, right? Because this one, so this one here is not at all like me, right? Because they're, they haven't rated any, so there's zero correlation between those two because they haven't rated any of the same ones. This one looks quite different from me, right? Because they actually ranked this item here a 1, whereas I ranked it a 4. And so those look very unsimilar. Whereas this one looks, again, trivial because there's only one item in common. But this one looks kind of similar to me, right? Because they've ranked this thing as a 4, and I ranked, or this thing as a 5, and I ranked it as a 4. So we're kind of similar in some sense. So let's talk about this a little bit more formally now. I'll bring up the document can for this. Okay, so in general, we're going to refer to our prediction on the ij element. So it's typically going to be an element that's not observed in our data matrix, right? This is something we're trying to predict. We're going to predict it in the following way in user approaches. And by the way, I'll later, this essentially is my hypothesis function, right? It's my prediction I'm making for my method. So I'll eventually call this something like, this could be called h theta of I, j. But we're not going to do that right now just because there are no real parameters to this first method here. So I'm not going to worry about that too much. Okay? But later, for matrix factorization, I will talk about a hypothesis function in this manner. So in item to item, in user to user, we make predictions in the following way. I'm going to say that this prediction, my prediction on my ijth element there, is going to be first equal to the mean prediction for the ith user, right? So this would be my kind of average prediction. And we include that because it turns out that different users have different kind of baseline ratings they give everything. So some people give everything a 5, some people give everything a 2. And it works much better if you kind of model not the absolute ratings, but actually the difference in kind of rating, right? So everyone ranks things differently, but people tend to have, this is still better than my average or worse than my average. So it typically works much better if you kind of scale things by a user's mean rating. So I'm going to do the following. I'm going to say this is equal to this plus the sum. Well, now I need to look over sort of the rest of the users here. But of course, I'm only going to look over the users that have actually, so I'm trying to rate item j, right? There's no point in looking at users that haven't rated item j, right? Because those are ones who are just users that they're not going to give me any information. So going back to our example here, and we'll look through this in a second. But going back to our example here, there would be no value if I want to rate this item here. There's no point in looking at ones that haven't rated that item that won't give me any information about it. So I'm only going to sum over the ones that have rated that item. So the way that we write this is that we write this as the sum over all k such that x, so this is all for all users k, such that xkj is not equal to 0. We're going to have the convention that 0 ratings are in fact missing here, but just important, those are not 0, they're just actually missing, right? Okay, so we're going to sum over all the users. Importantly, I'm summing over users here. So this k is a sum over users. Oops. Users. And the way you know it's sum over users is that I'm having k in the first index here of x. Okay, and x is always indexed first, users, then items. So I'm going to sum over all my entries here that are where this other person also rated this movie. And I'm going to include this wik term. And this term here is going to be a similarity, which we'll define in a second, between users I and k. Right? So I multiply this by a weight essentially, which is equal to the similarity of, in some sense or another, between users I and user k. And then I'm going to multiply essentially, what I'm trying to model here is, of course, the difference between my mean and the rating of this movie, this item. And so then I'm going to rate this multiply the weight by essentially xjk minus the mean for this guy. So minus the mean for the kth user. Okay, and then I need to make this, I want to normalize this, of course. So then I normalize, if I have to normalize it, I normalize by the sum of the weights here. Same thing, not equals 0, WIK. Oh, actually, there should be an absolute value down there. Sorry. These can be negative as well as positive. And so this is actually missing an absolute value. I think it just didn't, it somehow didn't show up there. Okay, so you actually divide by the absolute value here because there can be negative weights. So someone can be really unlike me in every way, so I actually use their weight negatively. But I still want to divide by the sum of their absolute weights. That sort of gives the total, possible amount of weight they could contribute to this prediction. Okay, does that make sense to everyone? Yeah. Has the what? So the question was, does the upper part have the absolute value as well? No, it doesn't. So the upper part is essentially, the upper part here actually says, if someone is a negative similarity to me, I actually want, so they always give the exact opposite reviews as me, basically. So whatever I call a 5, they call a 1. Right? I actually want to be able to take that into account and say, their difference in means actually should count against, my rating. So I should rate something higher because they rated it lower. And so I want to be able to have this term here actually be negative, so I can incorporate essentially reviews that are anti-correlated with me, which is very possible. There are definitely users that diametrically disagree always, and so you want to be able to incorporate that. But then when you divide, you still have to divide by their total amount, not by the because otherwise it could sum to 0, right? That's not what you want. You want to divide by the total amount. Yeah, question.
Why is it better to model the difference?
Yeah, so that's a good question. So the question was, why is it good to model the difference between the mean instead of just the mean itself? So, and this is kind of you don't have to, right? You could just have the actual ratings here. But what's been found is that people tend to have their own kind of personal scales about how much they like movies, period, and how just what they think it means to rate something a 5 versus a 1, right? So a lot of people will just rate everything a 5, and so that you can guess really easily what they're going to rate on something new. They're going to rate it a 5 always. And so it tends to work, but what seems to be the case, and this is, again, sort of an empirical thing, is it seems that people do kind of have similar ranges about how much, they say, a better 1 star better than my mean or something like this is still better than my mean, and 1 star below my mean is still below my mean. So essentially what you're doing is you're looking more at people's kind of relative ratings than their absolute rating to make your prediction. Yeah. Yes, this will remove so this function too we'll talk about will remove the mean as well. Or typically does. Doesn't actually have to by this definition. Doesn't need to, but it could. Right? So I should want to emphasize, so the similarity here could be something for all users, but a common trick to play is that you only look at the most similar users when you make your prediction. So I don't bother looking at everyone, because a lot of them are going to be around 0, right? 0 correlation between myself and anyone else. I just, if this is actually 0, it'll play no factor here. But you can actually save yourself a lot of time and actually improve your predictions somewhat if you ignore a lot of them, except the most similar ones, or the most unsimilar. Actually, to be fair, you could if someone always predicts the exact opposite as you, that's also useful. But it's typical to sort of limit yourself to only say k till the user's most similar to you. Okay, so this is how we make predictions here. And maybe I'll just edit this to. I think actually I copied this equation several times. I think they're probably all missing this. So the first one was, but there should be an absolute value there. So just put it in all the. I'll update the notes today. This one's actually hard to add in real time, but we'll do that. And then in general now, just know that they all will have that absolute value as well. Okay, so what do we pick for this weight function? And there are actually a couple things you can pick, but the most common, I would say, is this the Pearson correlation between two vectors here. And so this is sort of exactly what you expect. So remember, we actually already worked with Pearson correlation somewhat. I think on I forget which homework, but one of the homeworks we did. And so if you're on the Pearson correlation was sort of the correlation between two different, a number from -1 to 1 that would kind of capture how similar two vectors were, right? So if one was always positive, and the other's always positive and sort of going the same direction, same overall slope to the vectors, then these are going to have these are going to be essentially similar, and this is going to be close to 1 when these two things are. If they're identical, it'll be 1. If they are kind of as diametrically opposed as possible, so when one's positive, if you plot one for the other and the slope is negative, then they would actually be at -1, this correlation. And what it is it's just sort of the inner product of these two vectors with their mean subtracted off, and then dividing by the norm with their mean subtracted of the norm of them with their mean subtracted off. Okay, so this is just the standard correlation coefficient between these two, the ratings of each one. And so what we're doing here, so I'll just sort of say the Pearson correlation. What we're doing here is we're looking at this matrix X, right? I'm looking at the row corresponding to user I and the row corresponding to user J. And I'm just taking the correlation coefficient between these two rows here. Now the problem is that these things are not, normal correlation coefficients, as I mentioned before, don't have this notion of unknown entries, right? Every entry in a vector is known, and so you can compute correlation kind of exactly. Here, unfortunately, you actually have the case where a lot of things are unknown. So how do you do that? But what you do is pretty straightforward. All you do is you just sum over only those entries where they're this set IK, which denotes the items that are ranked by both the two users. So you only compute the correlation over the items that are ranked by both of them. Now this is not always done. There's actually other things which is kind of strange. People do it. They actually kind of ignore that, and they just compute them as if they're normal vectors anyway, calling all the entries 0 that aren't included there. And there are some sort of equivalences here. So if you first center these things, for example, or center if you first center the other entries, then if one of these two things is 0, it'll just be 0. So actually you can make them equivalent, but this is actually typically done just not in that way. It's just done with the raw vectors for cosine similarity. So know that people actually do though this is by far the more common one. People do sometimes actually compute things that are not centered. So you typically want to center them and only look at the ones that are they have in common. But people do omit that centering and look at all the ones they regardless of whether they have them in common or not. Okay, so let's actually do just a quick. And so again, the Pearson correlation. Actually, I won't write it here, but basically it's kind of what you expect. It's just the product of the two, sum over all the elements they have in common. The product of these two things, where you're subtracting off the mean of each of them. Divided by the sort of the norm of each of these things only on the elements that they share in common. Now, one thing that sort of is important here, yeah, question?
If you use raw cosine similarity and treating missing x0,
Yeah.
would that make, I'm not sure if it works out in the formula, but would that make like two users who share didn't rate anything in common?
Yeah.
But they have a lot of common zeros, right? But then, and two users who rated a lot of things, but one's 4, 3, and then 3, 4, still close numbers. And would that make the two users that sin long many movies be more similar than?
So I'm not sure to follow the whole thing. If they don't have any in common, then because they're treating missing things as 0, then this term will always be 0, so they'll always have 0 similarity if they don't watch any things in common. So here you're actually using the fact that 0 is sort of meaningful, even though it's not meaningful, because it will be 0 if they don't have anything in common here still. Yeah? There are two different users here, user I and user K. So this formula here is computing the similarity between user I and user K. Okay, and the way to know that is that we're always using I and K as the first index into our matrix here. Okay, so I and K are both users here, and J is a item. Okay, so J is always something over items here, and K is always something over users. Or rather, when we sum over this here, we're summing over users k. Okay? So it's a little bit confusing with the notation, and I sort of know. The way to remember which is which is to look at how they're used in this X matrix, because if they're used in the first one, they have to be a user. If they're the second one, they have to be an item. Okay, so let's just look at a simple example here. So let's look at the example we talked about before. So this is the poll now. If I were to use this method with Pearson correlation to predict the following point, so I want to predict this point here, what value would I predict for my for that missing element there? And it's also maybe kind of a hint that I can ask this in a poll, so you should not be involving too much complicated math here and square roots and all that kind of stuff. You can actually just do it pretty easily. Is the poll? Where is the poll? Let's see. It's not refreshing. Here we go. Okay, so let's open back up. So this is a this is one of the more uniform research I've ever seen. So I don't know what that speaks to. I think we could have had like random things there. We wouldn't have gotten so uniform than that. So maybe so maybe there's some issue here. Okay, so I don't think I'm going to bother asking this time. It's hard enough when there's a clear right answer here to ask. Okay, so let's just go through it. Or possibly the people were just thinking it would involve a lot of computation and they just clicked on a random response. Okay, so let's go through it. This one's fortunately very easy, and that's the idea, is that it was actually easy to do here. So the first thing to note is that there's only one row that actually matters, right? Because you're looking at other rows that rate this item that have non-zero correlation or non-zero weights, right? So the third row there, that rates the item, but there's no elements in common. So no matter what we use, that wi is going to be 0 there, right? This is going to have no correlation, so we throw that thing out. I guess by this it would be like 0 over 0, but we just call that 0. So the only row that's going to matter is that second row there, because the only one. I mean, the first one, shares some terms in common, but it doesn't rate that item, so we can't actually do anything with that, right? We only can use the second row. So all that matters is the second row of our matrix. And then the second row, all we do, and so we know that that's going to, that has weight, whatever it has. I actually don't even care. I don't even need to compute the weight, because we're just going to have that and divide by it, right? I guess it could be positive or negative because you divide by the absolute value there, but it's positive here, just FYI. Because basically what it is that these things are that. So what we do here, actually wait, did I get this wrong? Actually, is this actually 0? Okay, this is 0. I see. That's why it was so confusing. I messed this up. So this is okay. So it makes perfect sense now why everyone was correct, because it's actually undefined with this response is. So let's actually change one of these. Let's make this a 5 right here. So let me just say that. So okay, makes perfect sense. Now I understand why everyone read that wrong. Let's call this a 5 here. Okay. Let's answer the question. What would be if it was a 5? Okay. So okay, now I understand. So thankfully it wasn't just that this was it was actually an undefined question. So, okay, so if this is 5, right? If this is 5, then these two ones are both above their mean, so the weight's going to be positive. And so it's just going to be, essentially going to normalize out to 1 because you're going to have it in this denominator, the numerator divide by the denominator, so the weights kind of cancel out. So if this is 5, the mean here would be 4.5, and the mean there would be 3.5. And all that matters in this is that, essentially for that other row, how much lower than the mean is that item, and it's 1.5 below the mean, so you would actually predict 3 here for this one. Now, I was thinking you'd actually predict 2.5, but I neglected to account that actually the W's there are 0, so you predict nothing in this case. But hopefully it makes sense that in this case, all you would do is you would just look at the one entry there. I was actually just trying to ignore this, but then forgot the weights there for 0. You look at essentially the one row, and all you would sort of be looking at is adding my mean, which is in this case 4, to the difference there, which would be negative 1.5, so it would be 2.5. But of course, there's this problem that we don't actually have a valid weight there. So I guess I should have said cosine distance, and then that would have been defined. But oh well. Okay, so that makes perfect sense why this was such a tricky question. So again, don't worry that they just count your participation, not the actual answer. So that's very good in this case because that was a poorly defined question. Yeah, question. Yeah. Yep. Yep.
So for item 2, since user 2 has given rating of 2, so is it not a correct thing that user 4 will give a lower rating because for the same item, user 2 is giving higher rating?
Well, but right. So okay, so it's a good question. I won't repeat the whole question, but I think the idea was that look, it seems kind of strange that again, assuming this example is the case, actually this isn't 5. It seems kind of strange that this one. That we're giving a lower rating there, where shouldn't we give, because that one rated a higher one than that, shouldn't we give like a higher rating? Is that what you're asking?
So shouldn't we, like, user 2 is giving a higher rating for a similar product.
Yeah.
So if you use that, then user 4 should give a smaller rating.
Oh, I see. So the idea here is that user 2 seems more generous because they're giving a higher rating than the other user, and so they should have a higher rating. So that's true, but on the flip side, user 4 just rates everything really well, right? So they, their mean is higher than the other mean, right? So that's actually what's being factoring in there. Is that the mean of user 4 is higher than the mean of user 2, and so. Again, this is an assumption of the method. You can debate about which way you want to, how you want to do it. But the assumption here is that because their mean is higher, we're going to subtract their rating from the mean. Their mean is high now; it's 4, and so they would actually have a lower rating here because they would have a higher rating because this mean there is they have a higher rating because this mean there is 3.5 instead of 4. Okay, let's go back to somehow there. Let's go back to that. Okay. Okay. Now, actually, we're running out of time, so I won't dwell on item approaches, despite the fact that they were a little confusing initially. So what I'll say about them is that everything that I've said so far works exactly the same with item approaches. So the item approach. Is this exact same thing? Maybe I'll just write it here. I'll just write the first formula. So item approaches is the exact same thing, except we think about computing similarities between the columns in the matrix instead of the rows in the matrix. So if I want to make my prediction for x hat ij, that would be equal to x bar j, where this now means the mean rating for item j. Instead of the mean rating for user I. So if I want to rate j, I look at what all users rated that item, j, and then I add the sum over all k. And now k, importantly, sums over items, not users. So sum over all k such that x ik is not equal to 0. I sum over all the things that I've rated before, right? So this is me, user I here. So I look at all the things I've rated before. And I look at what I rated them minus what the average rating of item j is. And then I normalize by the same thing. Or sorry, I have a w here, wk, wjk, we'll say, divided by the same normalizing thing, where there again should be an absolute value there. So again, it's a little different. So before I sort of look at myself, to sort of predict myself, I would sum over, other, it's before rather, I summed over other items and says that, for users similar to me, how have they rated this item before? Here, sorry, for basically for users similar to me, how have they rated this item before? For the item approaches, it says, now I'm going to sum over all other users. sorry, I said that wrong. Here I'm summing over users. Here I am summing over users. So for all other users, and this item, how have they rated that item? For the item-to-item approaches, when I make my prediction, I'm summing over items here. So I'm summing over the items k that I've rated before. And I say, okay, so I've given these ratings before to the other items. How similar to these previous things that I've rated is this new item, right? And so this similarity score now is a similarity between, that's J there, the similarity between items and items, okay? So other than that, where's my mouse? Other than that, everything's the same. All right, the only difference is, kind of conceptually, instead of first finding users that are similar and then summing over all those users, I find items that are similar and sum over all those items. Right? Does that kind of intuitively make sense? Because we were sort of asking before. Okay, yeah. I think the big kind of conceptual thing is that instead of summing over all other users that have rated that item, I sum over all things that I have rated before, and then try to find the similarity between the thing I've rated before and this new item. Yeah?
Can't you combine the two metrics in like a weighted average?
Yes, the question was, can you combine the two in a weighted average? And yes, absolutely you can. So it is very common to use hybrid approaches here that have both these two elements to them. Yes. Okay. I have another poll question actually. I might actually skip this unless, because I already have one. Because I am running short on time here. And I want to get to the matrix factorization part because that's actually the part that's on the homework. So let me actually skip the next poll question. It was about kind of the efficiency of the different methods, about whether you want to use user or item based upon the size of your matrix. But I'll leave that kind of as an open question for now. If people are curious, they can ask on Piazza. But let's talk actually instead about matrix factorization. So the idea here is actually, we're going to kind of revert now to the notation we've used for the rest of machine learning. So the idea here is that we're going to, I mean, before I was sort of defining just how we make these predictions, but here I'll define it in a kind of a similar way, but we're going to actually need to more rigorously define kind of what the loss function is that we care about and how we optimize this loss function. So the big thing we're going to do here is that I'm going to represent my prediction, x hat ij, as being equal to the inner product of two vectors, being equal to the inner product of ui transpose vj. Okay? So here, ui, which is a vector, I use the word rk, this is rk, so this is a vector in rk, is a set, you should think of it as kind of a set of user-specific coefficients. All right? Oh, sorry, not there. Yeah, so UI should think of a set of user-specific coefficients. Whereas Vj, also in RK, and they have to have the same dimension because taking their inner product, right? I'm multiplying by their inner product here, or I'm taking their inner product. That is going to be a set of item-specific coefficients. So we think about this in some way. It's kind of like a linear model, right? So if I had some features that described an item, right? I don't have that here. I don't have item features like the way I normally do. But if I had some features Vj, I could form a prediction for me, how I would like that item by multiplying, some linear function with those features. So in other words, ui transpose times that. And similarly, if I was to flip, it was sort of inverted, and I had some user-specific features, I could form the prediction for any given item by taking also a linear function. So what we're going to do here, kind of interestingly, is we're going to learn both these two things simultaneously. Right, so we're going to learn kind of features or coefficients for both the users and the items at the same time. And we're going to do it in a way that makes our predictions close on the observed values. All right? And the key part here, of course, is that this, where we're constrained, is that this term k has to be much smaller than the actual size of the matrix. So if it was the size of the matrix, you could have any infinite number of possible values they could take on. But if you constrain k to be small here, that actually means I have to find some sort of lower dimensional representation of this matrix. And we'll relate this to PCA and low rank matrices in a second. But putting that aside for a second, with this kind of convention here, let's sort of adopt our standard machine learning framework for how we actually solve this. So the first thing we need is a hypothesis function, which we already actually defined. That's just this thing up the top. So that's just saying, our hypothesis, which is what we predict on ij, that equals ui transpose vj, where here, I'm saying h of theta, and here, if you think of theta as being all the parameters, our parameters here would be basically a vector of ui, so a user vector, for I from 1 to m. In our big matrix, we're assuming our matrix X is m by n here. So that means we have m users and n items. I should make that explicit. So X here is m by n. That means m users and n items. Okay, and our other set of parameters then is going to be these vj terms, and that's from j equals 1 to n. Okay. So our loss function. Okay, so that's our hypothesis. That's where we're going to make our predictions. All right. Question? Yeah.
Is there one in the vectors, or else you're just looking at the interaction terms?
Is there a 1 in the vector? Oh, in this, is there a constant term in the vector here? We don't need it. You can always. We're going to figure out. We can choose both these things here. So here, if it's good to have a 1, a constant term, you can always add it. But there's not by default here. That would just be equivalent sort of, you actually don't need it in this case. But it wouldn't, yeah. You could add it if you wanted, but you can always just, because they're both parameters, it will learn it if it needs to. Okay, the second thing that we're going to have is we're going to have a loss function. And here, we're going to just use the squared loss. But importantly, we're going to use the squared loss only over those entries we actually observe. Okay, so we're going to say that our loss is going to be just h theta ij, and the actual value here is going to be their difference. So h theta ij minus xij squared, because that's going to be our loss function. And then what we minimize is, and this leads to the optimization problem of minimizing over theta, which again really means minimize over u and v, all u and all v. The sum over, and I'm going to write this as the sum over all ij in S, which is just the set of observed entries. So minimize over all our observed entries of just this thing, the h theta ij minus xij squared, which this thing here just, of course, is equal to ui transpose vj minus xij squared. Okay, so that leads to essentially the following optimization problem of just minimizing over all u and, I should say, I didn't actually write it here. But basically minimizing over all u and v, the sum over all our observations, ui transpose vj minus xij. So what our prediction is, according to our linear model, but it's not quite linear because we have both those terms we're trying to learn, minus our actual observed value there. Okay, so the tricky part here is solve this optimization problem. So maybe I'll just write it here I had a few different versions there. So we're going to minimize over U and V, sum over all ij in our observed set of ui transpose vj minus xij squared. Okay, so here's the sort of key part here. Now, I should add, it is possible, and it's very common these days actually, to just minimize this by gradient descent. So you actually can compute gradients here, and I could just minimize this by gradient descent. However, it's actually for the purpose of this lecture, it's actually good to know, kind of maybe for historical reasons as well as for practical reasons. There's a very common alternative algorithm people use here, which is called alternating least squares. So it's called alternating least squares. So here's the idea. If I want to solve this problem here, and let's say that I actually want to just solve it for a single ui term. All right, so let's just say that I've fixed these vj's, whatever they currently are, and I want to solve it for a single ui. Of course, just to be clear on this also, you can flip the order of the inner product here. It's the same thing. So whether I put ui first or vj first doesn't matter. It's the same exact term. But if I want to think about kind of a restricted problem here, where I fix all the v terms and just solve for a u term, this here is actually exactly just a least squares problem, right? This is identical to a least squares problem. Okay? And it turns out, because of that, there, of course, is a solution that looks just like least squares. It ends up being this term here, where you basically sum over all the j, such that I and j are in your observed set. So remember, this is for a given ui here. So I sum over all the j's that sort of this user, all the items this user has rated. This thing here, that's the vj transpose, that's sort of the outer product of the item coefficients there, times vj times the target here. And that's exactly the same as our least squares solution, just for with the normal equations, just for the the case of vj being the features and ui being the coefficients. The other important thing here is that actually all these optimization problems are independent for all the ui's, right? So the idea here is we first set ui to be the minimum, or I guess I'll say the argument, right? It's the thing that minimizes over u minimize over u of sum over all ij in S of vj transpose u minus xij squared, which is equal to this thing here, sum over all ij in S, vj transpose inverse, sum over all ij in S, vj xij. Okay, so that gives me a solution for a single user's coefficients. And I can just do this for all I. Okay, so for all I set ui to be the solution to the least squares problem here. And now, as is hopefully sort of clear, because this is completely symmetric, you can do the same thing for the other case, right? So for the ui's being fixed, I can solve with least squares for all my vj terms. So for all j, vj is just the least squares solution. So actually, this is in some ways similar to things like k-means, where you sort of alternate between optimizing one thing and the other. So in k-means, we sort of alternate between optimizing which center every point was closest to, and then optimizing over the centers themselves, right? And so this is sort of similar, but it's actually even a little bit more symmetric, because they both just appear in the equation the exact same way. I first fix my features for the items, for the movies, and I solve all my user coefficients. And then given those user coefficients, I solve for all my movie coefficients. Okay? And in doing this, because again, just like k-means, every step I am minimizing a loss function. my total loss will only decrease as I repeat this procedure. So I can never increase my loss. I can only decrease my loss as I do this. Right? And so eventually you'll converge. Now it's important to note, and I think I have this in my next slide here. No, it's in the third one after this. It's important to note, and I'll just say this in a few minutes, but basically unlike, I guess, unlike PCA or algorithms that have an exact solution, here there are local optima, right? So you actually can, just like k-means, you can get stuck in a place where you have both bad features for both the users and the items, but you can't really get out of that hole there. And so it's important to note that this is just like k-means. This is a local algorithm, but it still will always decrease the loss. Okay, so just to highlight kind of the connection between this, and this is the algorithm. As I said, you can also use things like gradient descent to compute this, but it's very common just to use this alternating least squares algorithm. It tends to work a little bit faster in a lot of cases. But yes, but you might not get the global optimum in general. You won't find a global optimum. Okay, so I want to just now emphasize one thing about this. So what we're really doing here is that we are representing X as a low rank matrix. We're representing X as being approximately equal to UV, where here U is a matrix with all the user-specific features, see on each row of this. They're row vectors, all the way up to UM transpose. And V is a vector with the elements, the items of the features as the columns. So V1 is in the first column, V2 is the second column, etc., up to Vn. Okay. Now, importantly, this matrix here is going to be M by K dimensional, and this matrix here is going to be K by N dimensional. And as long as K is much less than M, which is always this M and N, which is always the setting we consider here, what we're doing here is we're representing X by a low rank matrix. So this matrix is the product of two smaller matrices, which are smaller, neither of which is both of which are non-square. However, and if you remember, actually, PC did something very similar here. But the big differentiation here is that we are only requiring X to match or to be close to that on the entries that we actually observe. So unlike PCA, we don't try to make all the entries match. We just try to make the observed entries match. And I just have one more slide that's sort of emphasizing this. The PCA also does the exact same thing. It performs a factorization of UV transpose. If you want the precise notation in the slides, we're actually forming a low rank decomposition of the transpose of X, but that's actually not really important there. Of course, they're just equivalent. But the big difference, of course, is that in PCA, because we are approximating X with a low rank matrix, but we observed all the entries in X, X was just our data matrix, it turns out, which I highlighted before, that there actually is this exact solution based upon an eigenvalue or a singular value decomposition of the matrix X, which sort of depends on this eigenvalue, very similar to an eigenvalue decomposition. And though we won't get into the details here, this makes actually for a very big difference mathematically. So PCA can be solved exactly, despite the fact that it's this weird low rank structure. Because all the entries are observed, it actually turns out you can solve this exactly. On the other hand, matrix factorization, because only some of the entries are observed, you are restricted in some sense to these approximate solutions. And so because of this, one thing I should say is very common is to initialize your features, your U's and your V's. You first initialize all the unknown entries in the matrix to be something like the mean value of the whole matrix. You then run PCA, and then with a full matrix, and then you additionally, from that starting point, you optimize the matrix factorization criteria using alternating least squares or some other method. So these exact approaches are a common initializer for more approximate approaches here. And the last thing I'll say is this approach really is it's very simple. In a lot of ways, it's actually much simpler than the user, the item approaches. But it's very powerful. And really, I think this technique alone by itself actually did improve upon Netflix fielded system that they had for a very, very long time. Doesn't get all the way to 10%. To get 10%, you need a lot of things, including temporal logic about how not logic, but temporal aspects of how movies and ratings change over time. But the winning team also, I believe, did combine approaches from both manufacturization and user-based, user-user, and item-item approaches. So as was sort of mentioned before, all these three things kind of provide differing views about how you think about forming these predictions, and they all can be sort of differently useful and useful both in isolation and together. Okay, and this is the one you're going to implement on the homework, though, for this people on 688. Okay, so next time we're going to talk, I believe, actually, I can't remember what's the lecture next time, but I believe it is anomaly detection next time. All right, see everyone next time.